This podcast is brought to you by LMU Munich.
In yesterday's second lecture, we saw the BCFW, the Brito-Cachazo-Feng-Witten on-shell recursion relations. And pictorially, diagrammatically, we had an expression for an on-shell amplitude, an on-shell tree amplitude, that was for a particular choice of the shift momenta given by a single sum over a product of on-shell tree amplitudes with one of the momenta shifted into the complex plane according to the solution for the pole. And there's a factor of the naive propagator supplied in there. And the shift is given in this case by, let's see what I choose in -1. So we have n-1. One thing that I neglected to emphasize last time, remember that we started by shifting two momenta, which don't have to be n and n-1, they can be any momenta, shifting two spinors by some amount proportional to the other label in the pair. And one of these was a lambda, the other was a lambda tilde, one a negative helicity spinor, the other a positive helicity spinor. But there's no reason that that has to be the helicity of the corresponding leg. At the moment, we haven't determined what constraints there are, if any, on the helicities of J or helicities of L. At this stage, it could be anything. So they're not linked to the helicities of the spinors that are getting shifted. Now, we can write this out in terms of an equation a little bit more precisely if you want something to program rather than a pictorial thing to understand conceptually. So we're going to define a special kind of partitions of the set of external legs into two subsets, and one subset, which I'll label P, contains J, one of the two shift legs, but L is not in P. Instead, L is in the complement of P, which I'll call P bar, and J, of course, is not in P bar. Moreover, we want these to be color adjacent, so they should be cyclically consecutive, so that they should stretch in some cyclically contiguous set. Of course, that means that they could contain objects from the something up to n, and then 1 through j, and then j through some I. And of course, the idea is that the combination of these two partitions should be exactly the full set of external legs. And we can then write the recursion relations in the form of a sum over all the different partitions of this type and we also have to sum over helicities of the intermediate leg. So I haven't denoted that over here. If you like, this is a product of two amplitudes and then the propagator. So we have, you can write it as spinors or as momenta. Since I'm using p, which you might confuse with momentum for the partition, I'll actually put in the momentum label here, and we ultimately have the shifted leg j, whatever leg we've chosen, and k here is the sum of all the momenta in P. Multiplied by the other amplitude, which has all the legs in P bar and contains the L hat index shifted according to the location that's determined by this set, according to this formula here for finding where the pole is located. So the notation here, P sub 1, means the first entry in this partition. And the -1, for those of you who are Mathematica fans, is inspired by Mathematica. It means the last entry in this set. So we basically just have, of course, all the legs in P. And then we also have one argument, which is the momentum flowing out of this amplitude and into the other one. And of course, on the other side, we have the other momentum. Now, we're allowed to choose J and L to be any two legs, not just adjacent legs as has been chosen up in the figure. But you can see that if I were to have chosen something other than adjacent legs, then there'd be another sum. I'd have a double sum because I'd also have to be choosing the legs in between these two to live on one amplitude or the other. So in general, it's not an ironclad rule. In general, you expect the number of terms to go something like the difference, the number of legs in between L and J, times something like n minus 3. That's the sum on the other side. So generally, it's advantageous to choose them to be adjacent if you're trying to minimize the number of terms. But there can be other reasons for choosing, making other choices. So the derivation basically relies on factorization and complex analysis. So in other words, you might say it relies on something which is extremely general plus almost nothing. That means you should expect this to hold for a very, very wide variety of applications. And even though I've been asking you just conceptually to think about pure gluon amplitudes just to avoid cluttering the notation or introducing any other extraneous issues, you can, of course, do this for fermions. You can do it for scalars, with some caveats about the behavior at infinity, which go away in supersymmetric theories. You can do it for gravitons. You can do it for particles with masses. And there are, again, some additional constraints and subtleties on choices of these shifted momenta, but they don't touch the core of the derivation. You can do it, you can supersymmetrize these recursion relations and do them in a manifestly supersymmetric form. And the thing that's a little bit different there is that in addition to conserving momentum, the way we did here, you can now imagine mixing some of the, shifting some of the Grassmann parameters as well in order to conserve supermomentum. And so then you can end up with a manifestly supersymmetric form, for example, in n equals 4 or n equals 8 supersymmetric gauge theories or supergravities. The other thing that you can do, and I don't know if he's going to do the derivation, but I think he will if he hasn't already touched on it, is you can shift more than 2 legs. And that's one way of deriving what are the so-called Kachazo, Svirchek, and Witten representation or recursions, which is something that I won't talk about in detail, and it's something that isn't maybe as actively used, but it is useful for deriving explicit forms for the singular functions that arise when you have multiple legs becoming collinear, for example, in gauge theories. And we'll come back and see the simplest form of those kinds of functions in a little while. So at this point, I wanted to run through one example, because it's always nice to look at explicit examples. And I'm going to pick one example which you've already seen at least one, if not 2, computations, the second being your own computation if you did the exercise that I suggested. It's always good to try out a new technology with something you know, because then you know what the answer is and it's easier to debug your understanding. And let's go ahead and pick a 2-3 shift in the notation of the previous lecture. And again, thus far, we don't know of any constraints on what the helicities of 2 and 3 have to be with respect to this shift. So in this case, because we're just starting with a 4-point amplitude, then we're really only going to have one diagram. It's only one way of putting 2 and 3 on opposite sides of the central propagator. And of course, it's the triviality that makes it simpler to do. So here I'll call the intermediate momentum P. And of course, we know from our previous evaluation of the 3-point amplitude, well, what do we know? We know, first of all, that we can't have all the helicities alike, otherwise we get 0 even if we're working with complex momenta. We know that we're going to get something non-zero for configurations where we have 2 identical and 1 opposite helicity, unless we do have complex momenta, but in fact one of these momenta is going to be complex, so there should be a non-vanishing value, and we actually have a hope of getting the right answer. I'm going to write this here symbolically as 1 over S34. And then we, of course, have the other momentum on the other side. And again, the momenta, my convention, are always directed outward. So it's going this way, and then all of a sudden it's flipping sign, so that's why there's a minus sign. Okay, let's just write down the formula for A3. So we have minus minus plus and a plus minus minus. So we have 1 2 hat cubed. And then we have 2 minus p hat minus p hat 1. And we have I over S34. And we have the right-hand amplitude, which is 3 hat 4 cubed over p hat 3 4p hat. So that's our starting expression. So the first thing that we'd like to do is just clean up some of these minus signs, which are maybe confusing the issue or looking confusing over here. Now, if I change the sign of a momentum in a Lorentz product, I get a sign. And so in a spinor product, which are roughly speaking the square root of a Lorentz inner product, I get a factor of I. And there's complex conjugation if you're going between the between these two. But in fact, if you're in the same kind of product, you don't even have to think about whether it's plus or minus I. It's just going to be overall 2 factors of I, so we're just going to get a sign over here. The other thing we can do is observe that it's been done very sneakily here, that it's actually the lambda tilde for 2 and the lambda for 3 that have been shifted. Remember that the other spinors don't get shifted. So I can simplify the calculation a little bit more. And the next thing we can do is observe that we can combine these two things. So P, of course, ultimately, we're going to want to replace P hat by P. P is not a massless momentum, so it's not quite clear how to get it into a spinor product. What we want to do instead is form these into a spinor string. So we have a P in the middle, and then, of course, we know exactly what to do with it, just a momentum. We can use Fiertz identities or whatever else. And you notice that there's an angle product and a bracket product. There's 2 of each, so we can put these together. Of course, for a massless momentum, there's no harm in just writing ij, jk. We can go back and forth and write it as I, j, k. And of course, for p hat, that's fine. When we want to ultimately remove the hat, we're going to want this form because that's the form in which it doesn't have to be massless. So there's 2 ways, really, of doing it. And because I've peeked ahead to the end of the calculation, I'll tell you that this is the more logical way to do it. I think in a few minutes, maybe to some of you, it's already obvious why I want to link it this way rather than the other way. So let's put these together. Let me just write it out again. Whoops, I'm missing a minus I over here. So let me also cancel off. I can rewrite this as an angle 4-3, bracket 4-3, and cancel off one of these powers. And of course, P just has some shift from the naive P, which is, let's say, K3 plus K4. But the shift vector involves, of course, angle 2, 3 and bracket 3, 4. So there's two terms here. There's a term which is the naive K3, 4, and then there's something which is plus or minus Z times 2 U3. So let's focus on this Z term. When we do the Fiertz identity, what's going to happen is we're going to get, in this case, an angle product of 2 and 2, in this case, a bracket product of 3 and 3, so it's just going to vanish. And it wouldn't have mattered if I'd arranged things the other way, but I would have had to do more algebra because that term wouldn't have vanished, and I would have had to figure out what Z is, et cetera, et cetera. Here, I can just do a little bit of algebra with the sponge instead of with chalk. Now we can just substitute in the value of P. Of course, it's, let's say, K3 plus K4. 4 is going to disappear because we have an angle product of 4 with itself, so I can replace this here with a 3. Likewise, over here, it's just going to get replaced with a 4. Now I'm back to having a massless momentum in the middle. So I can break it apart into spinor products again. Let me do that for this other factor as well. And I think you can see the sort of outlines of the final answer emerging. I have a square in the numerator. I have a square in the denominator, except that I also have a sign. I have to flip the two arguments. And now I get to flip two more signs over here and over here and rearrange things. And I get the answer that you already know is correct. Now, you may be inclined to say, well, this isn't very mechanical, and it's not the way a computer would do it. How would the computer know which of these things to link together and all that sort of stuff? So instead, you can imagine solving for the spinors p hat and just substituting them in. And I encourage you to do that, and I would encourage you even more to write a little Mathematica code to do that, and then you can be convinced that the computer can be taught to do it too, which is in some sense part of the purpose in these exercises. How many people here are Mathematica users? Oh. And how many people here are Maple users? A few lonely souls there. Well, you can do a lot with Maple too. I don't need to beat on it. I happen to prefer using Mathematica myself. Yes?
Did I get it right? If you want to write a simple expression for just half of the terms with a p hat, you won't be able to offer something nice, but you need the combination of the angular brackets and the square brackets in order to find the simplification.
Well, I mean, it depends what you mean by simple here. I think if you were just to write this, I haven't actually done it recently, so I don't remember what it looks like. If you're just to write this out, giving an expression for the p hat, it's not something horrible, right? I mean, it's still not that complicated. You could, in principle, just solve for this in terms of I mean, you could plug in the formulas for the shifted p hat and figure out what, you can still do that, right? There's nothing to obstruct you. This is just a little bit a slicker way to do it. It's not the way you teach a computer to do it, though, the way I did it. So that's all I'm saying.
More complicated situations, so you need a lot of experience in order to find this?
So when you're faced with, let's say, some expression, some rational expression in terms of spinor products, and you don't know anything particular about its factorization properties or its limits or anything like that, then yes, simplifying it is something you can teach a computer to do, but necessarily getting to the simplest possible form is a little bit of an art. So on the other hand, if you do know something about its factorization properties, and in general something that's, let's say, a coefficient of an integral or a term in an amplitude, you know a lot about its factorization properties, and that can help you guide yourself towards a simpler expression. If I remember, I'll remember to make that comment when we go back and look at factorization a little bit more in detail in probably about half an hour or so. Actually, a little bit less than half an hour, maybe 10 minutes. Okay, so people have asked after a lecture, and it's also something that arises naturally. The question is, what shifts can I pick? Am I allowed to pick arbitrary legs as shifts? And the one constraint we really have on that, remember that we wanted a of z to go to 0 as z goes to infinity. And it turns out that that allows you to determine that there are 3 classes of shifts that are okay at tree level, and there's one class that's bad. And here, the minus and plus now in the gluon case refer to the actual helicities of the corresponding leg. So these shifts are good shifts. And this shift is a bad shift. You'll notice that the shift I chose is precisely of this form. So it's a good shift. And so we didn't actually have to go and check that the z to infinity behavior is correct, because we can actually study that in general. You can also give an argument for these 2 shifts, but it's a little bit more involved. And the basic idea is that we want to think about doing a diagrammatic calculation. So again, when you're doing explicit calculations, you don't necessarily want to use Feynman diagrams. In fact, anything but the most trivial calculations you probably don't. But for arguing about general properties, it's sometimes still the right way to organize a calculation. And we'll do that in some of our derivations at one loop as well. So we want to think about doing a Gedanken calculation. Just imagine doing the calculation. We're going to do some power counting. So if we have a 3-point vertex that has one of the momenta being z-dependent, remember that the structure of that vertex had a momentum dotted into a polarization vector multiplied by 2 polarization vectors dotted into each other, and then a cyclic sum. So the 3-point vertex is, if it has z-dependence at all, is going to scale linearly in z. The 4-point vertices don't have momentum inside them, so even if there's a momentum flow that's z-dependent, these are still going to scale as 1. There's no z to the 0, perhaps I should write, just to make it a little bit more obvious. The propagators involve a momentum squared, so you might have thought that it should go as 1 over z squared, but in fact, it's always multiplying a null vector, so the z squared terms vanish, and the propagator itself, if there's any z dependence at all, is going to go as z inverse. So imagine that we have some place in the middle of the graph where we have 2 3-point vertices and some propagator in between them. There's going to be a z, a 1 over z, and a z. So overall, there's a z. If we compare that with 4-point, collapsing this to a 4-point vertex, then that would be z to the 0. So this is actually dominant. So having two 3-point vertices and a propagator with the z momentum flow flowing through them is going to give the dominant contribution. That means we're going to get the dominant contribution, the leading contribution in z, in the behavior of z, if we have a chain of vertices with propagators going all the way from j hat to L hat. And what is that going to do? Well, we're going to have, of course, we can add in additional 3 vertices, but we're always going to have one more 3 vertex than propagators. So we're going to have, overall, we're going to have z to some number, well, number plus 1, divided by z to some number. So overall, we get a scaling with z. That seems bad at first glance, because when z goes to infinity, z itself certainly does not go to 0. So does anyone see what I'm missing here? Very good. So we have to look at the polarization tensors, and the polarization tensors, of course, is also where we can end up with differences between the different choices of external helicities. So if we look at J with a negative helicity, then we can write its polarization vector using the spinor helicity basis. But of course, we know that it doesn't matter what basis we choose. This thing is going to get shifted in the denominator. So it's the angle bracket that's unshifted and the bracket that's shifted. So this thing is also going to go as z inverse. And likewise, if we look at the positive helicity gluon the polarization vector for L, then we're going to get something that again is shifted in the denominator, so it's going to go as z inverse. So we have z times z inverse times z inverse, and that actually does go to 0 as z goes to infinity. On the other hand, you can see that if I were to change the helicity, so for example, suppose I go to a positive helicity here, I lose this factor of z in the denominator. All of a sudden, this is going as z to the 0. Overall, the thing is going as constant, or at least this simple-minded argument says that. You can actually demonstrate by a more complicated argument where you do essentially one additional factorization that these two cases also have adequate behavior as z goes to infinity. But this case really cannot be rescued. So at tree level, you can make these choices in the gluon case. There's additional restrictions that one has to figure out once one includes fermions, because you also have to make sure there's an appropriate factorization in the channel you're choosing. So you can't, for example, choose two ends of the fermion line to be the two shift vectors. But basically, the same kind of argumentation about the helicities you can work out. And they're generically, there's always some choices of shift vectors that are okay. Okay, so let's go back and look a little bit more at factorization. And so far, we've been relying on something that's really very novel from kind of the traditional field theory point of view. If you opened a field theory book even circa 2000, then people wouldn't be thinking about factorizing in complex momenta, where the factorization is actually simple. You have a simple factorization for multi-particle amplitudes and a simple factorization even to remove a 3-point amplitude. We had looked at 3-point factorization very briefly last time. And let me just draw the picture again to remind you. So in the limit that the sum of these three momenta is going to 0, so long as we're not also getting the two-particle invariance, so long as the two-particle invariants are not going to 0, and we're avoiding the collinear regimes, then we get a factorization into a 4-point amplitude. And an amplitude with, if this started out with n legs, then this one will have n minus 2 legs. And I thought it would just be good to spend a couple minutes looking at, okay. Let's get that, keep this here. All right. Let's see if that actually displays itself. Okay, we can even raise this a little bit more so you can see the picture. Okay, so let's take a look at this amplitude a little bit. This is actually an actual computation. This is, in fact, quite an old computation dating back to the late 1980s. And in a sense, this is the simplest amplitude that goes beyond the class of amplitudes you've seen thus far, the so-called Park-Taylor amplitudes. So here we have 3 negative helicities and 3 positive helicities. And you'll notice that there are different kinds of invariants that appear. There's two-particle invariants, which of course you could factorize into angle and bracket spinners. So in a sense, all the elements there you've seen before. And there's now 3-particle invariants. Well, that's no surprise. We're expecting to see that kind of thing in a general factorization. Before we look at that, then there's a couple of comments that are worth making. You'll notice, for example, on the second line that there's no S56 in the denominator. S56 shows up only in the first and in the third terms. But in each of these terms, there's also a bracket 5, 6 in the numerator. So we can cancel that, and we could write this as just having an angle bracket in those two terms, and there's nothing in the denominator that's singular. There's nothing that goes to 0 in the limit that 5 and 6 become collinear. So in the limit that K5 and K6 are becoming collinear, maybe naively, I don't know if you have any intuition at all, but maybe naively you might expect this to go as 1 over S56 because that's what the propagator looks like. But in fact, what you're seeing is that in this case with these two helicities, it's just going, in some sense, as the square root of S56. It's going as 1 over the angle product of 5 and 6. Okay, let's look at the different 3-particle factorizations we can get. So there's one non-trivial class of factorizations we can get here. Of course, we could factorize 2 particles in various ways, but that's special. We know that A3 is going to give us trouble if we're insisting on real momenta. Again, here we're back to thinking about real momenta. But we can factorize 3 particles on one side, and then there'll be 3 on the other. So here, we're starting with 6, and we're going to end up with a 4-particle amplitude and a 4-particle amplitude and some propagator or some invariant in the middle. So there's one factorization that's very easy to understand, and that's because the corresponding channel is absent. So there's, of course, a variety of different three-particle invariants you might have. You could have S123, S234, S345. Well, if there are additional ones, but S456 by momentum conservation is the same as S123, so there's really only three distinct ones. And you'll notice two of them appear, S234 and S345, but S123 is absent. So that means that this pole term is actually absent. There's no universal term. All the terms that show up in that limit are non-universal. And can we understand that? Well, we can understand that very easily, because if we were to have a pole, let's imagine that we're looking for some pole in the 1, 2, 3 channel. On one side, we would have to have a 1 minus, 2 minus, 3 minus, and there's the intermediate state, which could be either plus or minus. But both of those amplitudes, when x is on shell, vanish by the first two Park-Taylor equations. So we understand exactly why the residue is vanishing over there. The other thing we can see is that there's a symmetry that relates the S234 to the S345. You can imagine flipping some of the momenta around and then changing the helicity. So there's really only one more channel to understand. And what are we actually going to get? Well, if we're looking, let's say, at the S234 channel, we're just going to get the very first term. And conveniently enough, instead of writing 1 plus 2 plus 3 in the middle, we could have also written it as 2 plus 3 plus 4. So that momentum in the middle, sandwiched in the middle of the spinor product, is actually a null momentum. I'll call it capital K here. So we can rewrite this term in the following form. We have 2, 3 times K4 squared. This is coming out of that spinor sandwich. And I've canceled the other angle 2, 3 against the S2, 3 in the denominator. I'm going to leave the S234 here as a reminder of what we're looking for. Again, one of the factors of bracket 5, 6, I've canceled against the S5, 6 in the denominator. So now we can start to manipulate this expression a little bit. We can multiply the first term, for example, multiply and divide by bracket K2. And over here, we can multiply and divide by angle K5. And we can now use momentum conservation separately on each side of the so we have 2, 3, 4 x, and on the other side we have 5, 6, 1 x. So we can use momentum conservation here to turn that into another K4. Now K4 cubed. We'd have 2, 3, K2, and we now have 4, 3. We cancel the angle product, and we're left with a bracket 3, 4. And this we can recognize as, of course, the amplitude for 2 minus, 3 minus, 4 plus, K plus. It's not the conventional way of writing it. It's the MHV bar way of writing it. But because we have two positive velocities, we can write it in that form. And similarly, we can use momentum conservation over here, and then we identify this object as corresponding to the 4-point amplitude 1 minus K minus 5 plus 6 plus here in the conventional representation where we would have, again, we use momentum conservation. Here we get a 1k cubed, and here it's in the conventional Park-Taylor representation that you've seen before. So that's an example of how the factorization works in practice. And at loop level, things are more subtle for multi-particle factorization, but at tree level, this is something that you can go ahead and use as a check, for example, on various calculations. That's always generally a good thing to do. Make sure that at least numerically an answer factorizes as you would expect. Now, the situation when we go back to the 3-point case is a little bit different. So if we were doing this in complex momenta, then we would have the same picture. There'd be a 3-point amplitude, a propagator, and an n-1 point amplitude. But we know that if we're working with real momenta, that we actually have 0. And of course, the propagator is also going to go to 0, so we have another kind of 0 over 0. And the question is, what is that object actually in practice? Now, we've seen that the vanishing here, and this, as I mentioned before, may seem a little bit to be playing fast and loose, but we can see that this vanishing is essentially linear in momentum. It's 1 power of a spinor product. And the pole, of course, is an invariant, so you might expect, roughly speaking, that you're going to get some behavior that's like this. So roughly speaking, it might be, depending on whether this was an angle or a bracket, this would then be either a bracket or an angle product. That's sort of the behavior you expect. And in fact, as I just pointed out to you, in the 6-point amplitude, if you were looking at a collinear limit, that's exactly the kind of behavior that you get. And I don't actually want to go through the full derivation, but in the collinear limit, you can, let's say if we're looking at momentum A becoming collinear with B, then we can write momentum A in terms of a collinear variable, collinear momentum fraction z, in terms of the sum of the two momenta. And similarly, the other variable we can write as 1 minus z times the sum. So the exercise is to evaluate the following object. You evaluate the vertex, the 3-point vertex divided by SAB. So this is the 3-point vertex involving A, B, and essentially A plus B, divided by SAB. Evaluate that using spinor helicity. And that will give you an expression for the so-called splitting amplitude. And that, in real momenta, is what describes the analogous factorization in the collinear limit. It's really a building block, very important building block for both for doing singularity resolution in real emissions and also as a very important check on properties of computed amplitudes. So the kind of behavior you get here, essentially you'll have one object which combines these two things together. So we have A and B. As always, there's a sum over helicities. So this is an n-1 point amplitude. And this is the splitting amplitude. Which you'll compute as an exercise. And if there's time tomorrow, then I'll go over this exercise then. Let me just say that. So I hope it's clear how you would actually write that out as a, yes?
So the splitting amplitudes, are they somehow, I mean, they're basically the same object as the splitting functions appearing in the Diagrammatic equation?
The splitting functions that appear in the Diagrammatic equation are in a certain sense the squares of these splitting amplitudes summed over helicities and particle types in a certain way. The splitting amplitudes generalize in a very nice way, and the factorization generalizes in a very nice way to one loop. And then the connection with DGLAP becomes a little bit more complicated. There is still one there, but it becomes more complicated. But at tree level, the connection is relatively straightforward. So there's a these factorization limits are universal, and you can simply translate that picture into an equation, which I won't write out for you. It's worth also looking just very quickly at what happens in the soft limit. So if you're looking at the full color-dressed amplitude, the full honest-to-goodness QCD amplitude, again, there's a simple factorization. Basically, you have to sum over helicities, but otherwise it's just a product of the amplitude. That's no longer true in the soft limit, but that's one of the original motivations for thinking about these color-ordered amplitudes, that if you look at a color-ordered amplitude in the limit that one of the gluons becomes soft, so its momentum is going to 0, then we have a factorization that is very much analogous to the splitting amplitude factorization, except that here we don't take the sum. The thing that survives in the n-1 point amplitude is not the sum of momenta, it's simply the amplitude with the soft gluon taken out. And of course, as always in these factorizations, there's non-universal subleading terms. Non-universal simply in the sense that what terms are there depend on the particular amplitude and on the details of the particular amplitude as here, whereas here, this form doesn't actually depend on the details of the amplitude, and in particular, this function is going to be the same independent of whether the other legs are gluons or quarks or what have you. And this function is again something that you might recognize in its squared form, although unless you've seen it before, you probably wouldn't recognize it in its spinorial form. It's just the iconal factor. Okay, so that's a little bit more about factorization, and what I want to do now is at least get started on the on-shell methods at one loop. And I think the goal today is to give you a little bit of background. Some of it's, in some sense, historical background, but I think it's useful for conceptual understanding of some of the more modern technologies, which we will see either at the end of the lecture today or tomorrow.
So this is plus.
I'm sorry?
HS equals plus.
Yeah. So this is the plus case. Sorry. And then the corresponding one, you just replace angle brackets with square brackets. Thanks. So I'm going to start by writing down the master equation, which in a sense is the most important equation you'll see all week. I don't know if Pier Paolo has already showed it, but it's fine to see it many times because it's the cornerstone for everything else. And we're going to see not the complete derivation, but how this equation would emerge. So we write in the unitarity approach and in various similar approaches the amplitude as a sum over an integral basis. And in general theories, there can also be additional rational terms. Now, we've studied enough that unlike maybe more general particle physics audiences, I don't have to say, well, it's roughly rational. These coefficients of the integrals and the additional rational terms, if any, are exactly rational functions of external spinor variables. And the way we're going to compute these is by unitarity. And at one loop, it's unitarity in 4 dimensions. We probably will not have time to see anything more than a brief overview of how these can be computed, but basically one way of doing it is with unitarity in 4 minus 2 epsilon dimensions. You can also do, in some cases, you can do certain kinds of recursion relations, but I'm not going to talk about that technology. These integrals are supposed to be a linearly independent set of basis functions, and they are what tell us that we're still working in a field theory. And again, the derivation of them will make use of a what-if calculation starting from a Lagrangian and Feynman amplitudes. And at one loop, this basis is going to contain various box integrals, various triangle integrals, and bubbles, at least if we're just working in a theory with massless particles. There'll be tadpoles in addition if we're working in a theory with masses. So in a sense, the OPP approach, which is what I believe that Pier Paolo is teaching you about, is focused to some extent on reconstructing the integrands which go into these integrals. We're not going to be interested in that. We're interested in getting to the final answer with as little detour as possible. We're really just interested in calculating these coefficients Cj, because in the greater scheme of things, certainly at one loop, this set of basis functions has been known for a long time, and it's a universal basis, meaning that any process you come up with, there's no new basis integrals you have to figure out, or you have to figure out what the basis integrals are going to be. And that is pretty much the situation by now at 2 loops as well, not necessarily at higher loops. On the other hand, these coefficients do depend on the process under question, and that's really what our work is to calculate. So again, the philosophy is to take general properties of field theory or general properties of amplitudes in field theory and to turn them into a tool for really doing explicit calculations. And the property that we're going to be relying on here is that of unitarity. So unitarity is again a very basic property in any quantum field theory. It just says that the probability is conserved, or in other words, that the S matrix is unitary. Actually, was the S matrix first written down here in Munich? Or was it somewhere else? Well, maybe it was written down here. I actually don't know that bit of history. I'm sorry?
We were too young.
Well, I mean, even I'm too young to know, to witness that. But I'm sorry? No, but doesn't the S matrix, go back to the 1930s or so? Yeah, I don't know, Sommerfeld or Heisenberg. All right, that's another homework exercise, is to Google the origins of the S matrix and see. I'm sure it didn't happen in this very building, but somewhere nearby. So if we think instead in terms of the transfer matrix, where we remove the forward scattering part of the S matrix, then this condition simply tells us that T minus T dagger can be written in terms of the square of T. Or if I'm playing a little bit fast and loose with the phases, then we have the imaginary part of some element, I guess there's a factor of 2, is written in terms of the square summed over all intermediate states. And if we put in the Feynman I epsilon prescription, then we can write this as the discontinuity being equal to its square. So this is a great starting point for some perturbative approach where you're trying to recycle things that you've computed at one order into a higher order, because it's saying, for example, if I'm looking at some one-loop object, then it's going to be written in terms of a tree-level object, or some two-loop object is going to have some terms that are, let's say, products of trees in one loop and so on and so forth. So it's exactly the kind of equation you can imagine bootstrapping, starting at some low order and marching upwards. Okay, we have the absorptive pieces. That's essentially what this discontinuity is. And if we were thinking in some very old-fashioned way, a la Kramers and Kronig, we could imagine reconstructing the real parts by using dispersion relations. And in fact, people have actually even done this explicitly for a 4-point one-loop amplitude. There's a paper of Brandhuber, Travellini, and Spence in which they do that. It's not necessarily the easiest way to do it, but it is possible. So we could write down some kind of dispersion integral, which I'm just going to really write down qualitatively. And the real issue, and of course where things foundered when people thought about doing this a long time ago, is that there are in general subtraction constants if this object is not well behaved in the UV. But the basic idea is that ultimately we know something more about the amplitudes and that they're arbitrary real functions. We know something about their analytic properties in the complex plane, and that knowledge of analytic properties is going to allow us to reconstruct the amplitudes. So you might call this sort of version 0 of unitarity. It's like an alpha release of unitarity. You can't really release it to the customers, but it's something you have to go through. And if you want a pictorial representation of it, then you can imagine thinking about the complex plane and thinking about there being some branch cut, and you're basically reconstructing a logarithm from its discontinuity. That's kind of the model of how the basic unitarity approach is going to work. Yes, good. I'm glad someone's paying attention, even if I'm not. correct. So the next thing we should do, since we know that we are working in field theory and we do have Feynman integrals lying around, we should think about how this works at the level of a Feynman integral or even a Feynman diagram. Fortunately, we don't have to work this out in detail. It's not that hard really at one loop, but at higher loops it's a little bit trickier. We don't have to do this because a very nice fellow named Dick Katkuski worked this out a little over, actually a little under 50 years ago. And what he taught us is that if we're interested in the discontinuity in a certain channel, a channel in which a certain momentum is flowing, we have some higher loop Feynman. Actually, let me just think about a single diagram here. So let me actually not do that. So this is just some higher loop integral or diagram. So we have some number of external legs, and these together have momentum k flowing through them. We're interested in the discontinuity in that channel. Then we have to sum over a certain set of cuts which isolate that channel. And the diagram on the right, before I draw the cuts through it, is supposed to be identical to one on the left. But since my drawing abilities are limited, which is why I became a physicist rather than an artist, then that probably won't be exactly true. In any event, you're supposed to sum over all cuts that isolate that diagram, isolate this channel. And there can be many different ways of doing that in general. What's meant by cutting here is to take a propagator that you're cutting through and of course we're living in the 1960s, so everything has a mass and is well behaved in that respect. And we want to replace it by a certain delta function which has a plus subscript, and really all that means is that it's an on-shell delta function where the energy is required to be positive. So we can write this out a little bit more explicitly at one loop, and then we can see how this is exactly the translation of the more abstract equation we started with. So let's imagine we're looking now at one loop. So we have some one loop integral. This is a single diagram. And let me label the legs as follows. And k here is going to be a notation that I'll use over again as so the subscript just mean to sum all external momenta from the first to the number j minus 1. So we have the various propagators running around the loop. And of course, the two propagators that we want to cut are the one just before leg 1 and just after j minus 1. So in other words, just after label L here. Of course, that by momentum conservation, the propagator going over here is L minus k. So we're instructed to do is to replace these two propagators by delta functions. So let's do that. Now we can do one more thing, which is to introduce momenta P1, which we'll call L, and P2, which we'll call L minus k. So of course we should introduce a delta function to ensure that momentum is conserved, and we should also introduce an integration to enforce that delta function. So let me put that in over here, just a little bit of room. And we can now simplify this. It's 2 pi delta of P2 squared minus m squared times theta of the energy component. And that gives us enough room to slide this down onto the line. We can also, of course, replace, I should say we should replace this with P2, and this we should replace with P1, P1. So we can now recognize, at least I hope people recognize, the object that we've created, which is split into two pieces over here, this and this over here. These two together are, in fact, the Lorentz invariant phase space measure. For two particles. So if we imagine splitting this object into two pieces, so again, we've put these lines on shell. So we have a tree diagram over here and a tree diagram over here. I'm taking the discontinuity in that channel, so that's the discontinuity of T. And it's a tree diagram times a tree diagram. So it's essentially the square, in some abstract sense, of a tree diagram. And we're integrating it over phase space. We're integrating it over all intermediate states. So this discontinuity is simply the Lorentz invariant phase space integral of tree diagram 1 times tree diagram 2. So if we wanted to, so that's all very well and good if we have the one loop amplitude and we want to compute its discontinuity by some other means in order to check, just 1 second, then we can write down this expression integrated over phase space. Of course, ultimately, we don't know the one loop amplitude, or just we don't know it yet, and we want to have a way of computing it. So what this is saying is that we can write down its discontinuity by taking a tree diagram, which we do know, multiplying it together, integrating over phase space, and then in some fashion or other, which remains to be seen, we do a dispersion relation and we get the complete one loop amplitude. Yes, question?
Yeah, I must admit, the actual assumption that this is passed for me, did I get it right that you replaced two propagators by their discontinuity?
Yes.
And how did it happen on technical level with a second momentum integration?
So what I did is, I mean, that's the reason I did that was to allow you to recognize it as a phase space integral. It's, of course, mathematically identical. What I did is I introduced a second momentum to be L minus k, and then I put in an integration over that momentum with a corresponding delta function to enforce this constraint. So I've just rewritten the second momentum in terms of a second phase space momentum.
The right-hand side of the yellow box is a clever insertion of unity.
Not the whole thing. This came from actually doing the cut, and the rest of it is a clever insertion of unity.
Left half.
Yes?
But the 4D delta function is not part of the phase, right?
It's not part of the...
Of the phase space?
Well, I mean, it is in the sense that I would say it is. I mean, since you want to enforce that the sum of momenta in phase space is equal to the original momentum flowing in.
I guess what worries me is that the two things look different.
There is on-shellness and total momentum conservation, right?
Right. So this is total momentum conservation, and this is on-shellness of the final state particles. This should have been a P1, I'm sorry. Okay, so we're starting to see the outlines of how we might proceed, but there are a number of problems which we should keep track of for our derivation. So first of all, this is done diagram by diagram. And we know from our discussions at tree level that that's a bad idea. All the particles here are massive, and we want massless particles, but those have all sorts of divergences which we have to handle. We have only absorptive parts, but of course we want the entire amplitude. And finally, I'm talking about a single channel here. An amplitude is many channels. And so our goal now is to slowly remove these problems, which we won't, of course, finish today. But as we're going along the way, we'll discover some other problems, and some point or other in the middle of tomorrow's lecture, we will resolve the last of those problems, and then we can do a few examples. So let's continue a little bit longer by doing some calculations in the abstract, not actually getting our hands dirty with explicit spinners or explicit results for a minute. And think about proceeding now to the level of amplitudes rather than just of a single diagram. So now let's imagine that we're no longer looking just for the discontinuity of a single diagram, but we're looking in a fixed channel for the discontinuity of a one-loop amplitude. Of course, we know how to write that amplitude in terms of Feynman diagrams. We have to write down all one-loop diagrams with the required external states, and we take their discontinuity and sum them up. Now, the first problem we run into is that here I've picked out a diagram which has both of those propagators that we want to cut, that surround the channel. But of course, in QCD, we have, for example, 4-point vertices, 4-point Feynman diagrams. And it could be that these two legs are joined together in a 4-point diagram. So how am I supposed to go about isolating channel K in that case? Well, we have a propagator that's missing there. Okay, let's multiply and divide by that missing propagator. Remember that Krutkowski doesn't tell you really anything about the numerator. He's just ignoring the numerator. The only thing he's really looking at are the propagators. So let's do that. Let's ignore this for a minute. Just some numerator that we're just going to carry along. And let's multiply. Let's replace the propagator by the positive energy delta function. So of course, this thing is going to give us 0. So what that tells us is that if the propagator is missing, we don't get a contribution to this continuity in the given channel. And it turns out later that that's also the fate of terms that are in a sense off-shell. If you have some term here that's off-shell, you can imagine expanding the numerator around the on-shell point. And of course, any of the off-shell terms will have some power series in this expansion parameter, so they will also give you no contribution to the cut. So that tells us that we should replace this sum here with not over all diagrams, but over diagrams that have two propagators isolating the given channel. And that's good, because that now tells us that we have a natural way of breaking apart every single diagram that appears on the right-hand side. And it also means that we could choose to enumerate those diagrams by first enumerating over all the different ways of having the Feynman rules on the left-hand side, and then over all the ways that we could have the Feynman rules on the right-hand side. Moreover, in each of those diagrams, we can then apply this, this cutting approach of Krutkowski. So that tells us we're going to get a phase space integral over the sum of all the tree diagrams on the left multiplied by a sum over all the right tree diagrams well, we know what this is, right? And we know what that is. We're summing over a complete set of tree diagrams. That's just giving us an amplitude. So that gives us the following kind of approach. Again, what we want to do really is not drive the equation this way. We want to drive the equation the other way. But you can drive an inequality either way you like. So we compute these tree amplitudes. And you could compute them using BCFW, but you could also compute them by other means, Behrens-Hiller recursion or other approaches. Then you form this Facespace integral. Now the Facespace integral has these positive energy delta functions in it. But that's okay. We can just go into the integral and replace those delta functions with propagators. So that would now give us back a loop integral. So there's a propagator on one side. There's the on-shell tree amplitude on the left-hand side. There's the other propagator promoted back from the delta function. And there's the other tree amplitude on the right-hand side of the cut. And this object, by construction, has the correct cut in the K channel. It doesn't necessarily have the correct cut in other channels. So we should do some algebra at this point in general to simplify the numerator and perform the integral reductions. And then we should identify the Feynman integrals. And the next thing we should do is replace 4 by d here. D, of course, is the usual dimensional regulator. Is everyone here familiar with dimensional regularization? Let's have a show of hands who is familiar. Okay, I think that's essentially everyone. Might be some people who are asleep, but that's all right. It turns out at one loop that the difference in some sense between these two things lives in the rational terms. So that at least as far as isolating parts that really do have branch cuts, that do have absorptive pieces, this is the correct thing to do. Of course, at this point, we've done all the numerator reductions, so we've identified the different Feynman integrals. We can now actually do those Feynman integrals. And when we do them, we'll have elements that are members of our basis, and there'll be some coefficients in front that, that are rational in terms of the external spinors. We're not done, though, because this thing, as I said, has the correct cut in the channel we're looking at, but it might have spurious terms that have incorrect cuts in other channels. So first of all, we need to retain only the terms that have a cut in K. And we need to sum over all channels. But there's a delicacy here in summing, because if we look at some integrals, and we'll come back and see this in a little bit more detail tomorrow, but you imagine looking at some box integral. Well, this integral has cuts in many different channels. It has a cut, let's say, in the S channel. It has a cut in the T channel. It has a cut in the channels corresponding to these two invariants as well. So if we were to simply blindly sum over all different channels, we're going to be overcounting contributions of integrals which appear in multiple channels. So that's why the sum here is in quotes. We have to sum, but making sure we take only a single copy of each integral which appears in multiple channels. So you can see that there's various things here that are something that you really need to do analytically. So you need to do the numerator reductions analytically, and this summation you're also needing to do analytically in a certain sense. But we've managed to cross off some of the problems on our initial list. We're doing things at the amplitude level now, rather than diagram by diagram. We've reintroduced dimensional regularization, and we'll see the three different roles that it's playing here. We're back to having full loop integrals, not just discontinuities, and we've seen more or less how to merge the different channels. So we can handle objects that have many different channels. There's another problem that we've uncovered, which is that we have to do some reduction algebra on the numerators in order to bring us into the form that we want in terms of a standard basis, because there's no particular reason when we multiply these tree amplitudes together that we're going to get something which is manifestly the right form. And we'll see how to overcome that problem tomorrow. This is what you might call version 1, or the first release of the unitarity method. And it's not just a pedagogical tool. It's something that was actually used to do a large variety of calculations in the 1990s, including some calculations of the all n amplitudes in supersymmetric theories, which then led to the discovery of a lot of other properties. So let me stop here for today, and if there are any other quick questions, I can try and answer them now. Otherwise, if the questions are more lengthy, then please do come back and ask them again tomorrow. Are there any quick questions?
Do you have a base of integrals for loops?
Yes, there is a basis of integrals for two loops, or at least it's understood exactly which integrals live in that basis. The thing that is not available, let's say, as a bit of Mathematica code is telling you exactly how to reduce some complicated numerator into a specific set of basis integrals. It's understood how to do that in principle, but there's no code that you can do that at one loop. There are existing codes that will tell you if you have a specific function in the numerator of your Feynman integral, this is exactly the terms that it produces in the final result. Of course, that's irrelevant at this stage because here all you need to know really are what the basis integrals are. And at that level, at two loops, you do know that.
I don't know if it's quick or if it's correct, but you said about the reduction algebra on numerators. Okay?
Yes.
So imagine you have a box that has a numerator, let's say
Right.
linear. So now we know that this is a scalar box and plus and triangle.
Yes.
Okay, now if you, but as you said, this Kapkowski things does not care about numerators. So if we take some discontinuity on the box only, do we miss contributions? If we don't do the reduction?
In general, the answer is no, but in general, let's think about it before and after reduction. So before reduction, there's just a box, but it has some numerator, and you're going to put that numerator on shell, and it's going to decorate what would otherwise be a scalar diagram on the left and the right. So it's not just going to be, so instead of writing down that phase space integral with 1 everywhere, I'm going to have to write down some function of P1 and P2. The other is, suppose I do the reduction first. Well, now I have two terms. I have, let's say, a box and a triangle. But in general, I'll be able to cut both of those terms. And so I'm going to have one set of contributions that involves additional propagators in the tree diagram when I integrate over phase space. And in the second contribution, I'll have fewer, but I'll still have the contributions coming from that triangle. And in fact, the contributions you would get, imagine taking that phase space integral. It has some numerator. You can do reductions on the phase space integral as well, and you'll get the same answers from the second form. But it's a good question, and we'll see how to separate those two tomorrow.